So the next method is speed control by adjusting the armature voltage, right? So as you can see, according to the equations, right, so this is the one that we are going to change VT, right? So this is extremely efficient method because it has like high control, speed control in here, right? So we consider, so the control variable is the armature voltage of the motor, which is Vt as we have written here. So this is the one that we are going to control, right, which is depicted as an adjustable voltage source, right? So here this is the adjustable voltage source. So okay, when the armature voltage is reduced, the no load speed omega naught is also reducing, right? For the same value of the load, torque and field flux, the armature voltage does not affect the speed drop, right? The slope of the speed torque characteristic is Ra over K phi, the total one square, which is independent of the armature voltage. Hence the characteristics are parallel lines. Field voltage is assumed to be unchanged, so this is unchanged, right? The field voltage, it is unchanged. So you can see these characteristics here. This is omega and this is torque, right? So what is the gradient in here? When we have omega equal, it is minus Ra K phi squared into Td plus Vt over K phi, right? So this is the gradient and this is the intercept, right? So when we change Vt, right, when we change Vt value, what will happen is the intercept will also change, right? So the higher the value of Vt, we will have the larger intercept. So that means in here that is for the largest voltage, right? And as you can see the gradient, right, this is not affected by change in Vt. This is not affected. So therefore, can you see these are parallel lines, right? So here these omega 01, omega 02, omega 03, omega 04, they are the no load voltages, no load speeds, and if we consider constant TD, you can see the operating points 1, 2, 3, 4, how they are changing. So for the in here, like at V4, that means at this point the motor is holding, that means it is not moving, the speed is equal to 0, right? So here these voltages are increasing, right? Voltages are increasing. So if you want to let's say if this is V1 is our rated value, that means the voltage that we can supply to the armature, right, the maximum value, right, then V2, V3, V4, they are lesser than that. So we are not going to talk about increase in the Vt than the rated values. Right. So then we'll talk about the next method as well, right? Controlling the speed by adjusting the field voltage. So field voltage means, so we can control Vf, right? We can control Vf. Here can you see in here Vf is controlled, right? So Vf is equal to If into Rf, and it is the field. Field means it is effect in our flux, right? So according to these equations, motor speed is dependent on field flux, which is phi, right? The no load speed is inversely proportional to the flux, right? So what is the no load speed? No load speed, that's it is omega naught, it is equal to Vt over K phi, right? So it is inversely proportional to the flux, and the slope is inversely proportional to the square of the flux, right? Here can you see that again, if we write omega equal minus Ra K phi squared Td plus Vt over K K5, right? So you can see no load speed means this is the intercept value, right? And here this is the gradient. So can you see gradient is inversely gradient is gradient is inversely proportional to 5, right? It is proportional 1 over 5 squared, right? So like that, right? And the intercept, it is proportional to 1 over 5, right? So intercept, it is proportional to 1 over 5. So therefore we can assume that since both parameters are changing, the change in the field voltage, it has a larger effect than the other two methods. So we can just assume, right? So we'll see what is happening, right? So as you can see it in here, so this is what is happening, right? Okay, so here we have the linear relationship between omega and the torque, right? And therefore these are the what will happen to our no load speeds. They will increase, right? So can you see that here if we here this one, the intercept, it is inversely proportional to 1 over 5, right? Can you see that they are increasing, right? So they are increasing, and the gradient, can you see the gradient is changing like this, because it is again inversely proportional to 1 over 5 square, right? So therefore the field voltage must not exceed the absolute maximum rating, right? And also since the DC motors are relatively sensitive to the field voltage, right? So that's why I said, because it will affect to the intercept and the gradient both. That means there will be high control when we change this field voltage, right? So the large reductions in field current may result in excessive speed. So that means here if we talking about the no load speed, so it is like this, right? So therefore if we further decrease this, what will happen is this will increase, right? So if we further decrease this one, the no load speed will go up to a level that is no longer controllable. So therefore we have to extremely take care of when we are changing the field voltage, right? So because the armature current is inversely proportional to the flux, right? Ia, which is equal to TD over K5, reducing the field results in an increase in the armature current, right? So again, right? Again here, think that when reducing the field, right? So when we reduce the field, right? What will happen? Ia will increase, right? Ia will increase according to this, right? So therefore we have to be extremely careful when we are changing the field voltage, because it is directly affecting to the flux, right? So consider this example, right? For 20% increase in the armature voltage, right? So here we are talking about 20% of increase of armature voltage, right? Then calculate the percentage change in the no load speed. So okay, assume that the load torque is unchanged. Repeat the calculation for 20% reduction in the field flux, right? So first we'll consider increase in the 20% increase in the armature voltage, right? So for no load, TD means it is equal to 0, right? So therefore here this is no load voltage, so we are not changing anything. So therefore omega value, it is proportional to the voltage, right? Armature voltage, right? Armature voltage. So therefore first it is 1 and now it is 20% increase, that means 1.2, right? So therefore omega 02, that means no longer speed at the second option, it is equal to 1.2 of omega 01, that means the initial value, right? So therefore what you can see is speed increases by 20% if we increase the armature voltage by 20%, the no load speed, right? No load speed, right? Then according to this, what is the no load speed? No load speed is the same value Vt over k phi, right? K phi, right? So at this point we'll take Vt constant. So k is a constant, so therefore omega 0 1 is proportional to 1 over phi 1, omega 0 2 is proportional to 1 over phi 2. That means omega c, we can write this relationship, omega 0 1 over omega 0 2, it is equal to phi 2 over phi 1, right? So it says the previous value is 1 and it is changed by 20% and it is reduced by 20%, so 0.8, right? So therefore if you calculate the second second change, right? So you can see how the speed has increased. It has, even though we have decreased the field by 20%, the speed has increased by 25%, right? So this is a 25% of increase that we are observing in here.